Hi everyone. In this lecture, we'll discuss about the Fourier transforms of signals. The idea of Fourier transform, meaning expressing a signal in terms of sinusoids, was thought of by Fourier in early 1800s, but we actually put it to good use only in 1900s when all the inventions of radio, telephony, television, all these things came into existence. We need mathematical tools to analyze signals that are being processed by all these applications. Okay. So for that, this was in fact all the engineers at Bell Labs. We should give them the credit. They are the ones. I mean, they literally resurrected all the mathematics that was invented almost 100 years ago by the likes of Fourier and Laplace, and then they applied it to engineering problems. So if I have a signal x of t, then I can multiply it with a complex exponential. This is equivalent to taking a projection and then integrate it over all time. So I'm projecting x of t onto a complex exponential of frequency f and computing a value. So then if I keep varying this value of f, I keep sweeping the value of f in a continuous way from 0 to minus infinity to plus infinity, I'll get different values of this function. For each value of f, I'll have to do this integral. Okay. Then I'm projecting x of t onto different complex exponentials and computing x of f from that. Okay. Then x of f is said to be the Fourier transform. Now this x of f is actually a unique Fourier transformation, meaning any one time domain signal will have only a corresponding uh, only a single valued x sorry only a single x of f. Okay, so which means no two signals can have same Fourier transform. So that's the uniqueness theorem. So that is actually which says that any signal can have only one corresponding Fourier transform. So since there is a one-to-one mapping between the signal and its Fourier transform, if I know the Fourier transform of the signal, I can recompute the time domain signal because there is a one-to-one mapping. Okay, I can easily recompute what the time domain signal is. So this using this equation, and that's called the synthesis equation because you're able to synthesize your signal from its Fourier transform, the value of its values of the Fourier transform. So this signal, the first equation is called the Fourier transform equation, is called the analysis equation because sometimes, most of the times, we use x of t, we use Fourier transforms to analyze a signal. Sometimes what you cannot infer from time domain, by taking Fourier transform, you can interpret a lot more than that in frequency domain. Okay, you just take a bunch of sinusoids and then add them in time domain. They look very random. The signal will look very weird. But if you go to frequency domain, you can clearly say what are the frequencies present in it. Okay, so that's one quick way of looking at it. And Fourier transforms exist for signals which obey this property, which is the energy of the signal has to be finite. It's called the Lebesgue integral. Fourier transform exists, meaning if you compute the Fourier transform of a signal x of f and try to plot its magnitude mod, because again, I'm multiplying x of t with a complex exponential, which is a complex number, e power minus j 2 pi f t. It's actually a complex number, and I'm multiplying with a complex number and integrating it. So the resultant x of f can be a complex number. Okay, even though x of t is real, x of f can be complex. Okay, so that's why I will take modulus of it. I'm plotting the magnitude spectrum for any value of x of f to not blow up, meaning for the spectrum to not contain points where it's going to go to infinity. Your signal x of t should be a finite energy signal. Okay, in fact, this is a more tighter condition, I would say. So for example, let's look at this equation. This is integral x of t e power minus j 2 pi f t dt. This is your Fourier transform. Now this will always be less than or equal to integral x. If I take modulus of this function, it's always going to be less than that. So that will be less than mod of x of t dt. So because mod of e power minus j 2 pi f t is 1, so I'll say that, I'll ignore that. Okay, so you'll get this result. Okay, so this, if you satisfy this condition, integral mod of x of t dt, if this is less than infinity, so now this value is called absolute integrability. This condition is called absolute integrability. You take the absolute value of a signal or the modulus of the signal, okay, and integrate it for all time. Okay, then if that value is less than infinity, then the signal x of t is said to be an absolutely integrable signal. So for such signals, Fourier transform, the magnitude of the Fourier transform will not blow up to infinity frequency, at any frequency f. Okay, it comes from that. As I said, this is a more tighter constraint. square of it should also not, it should be less than infinity. That's a more tighter constraint. Okay. Now we will look at some properties of Fourier transforms. So let's say first thing is we'll assume x of t to be a real signal. So the signals we process in the real world, for example, in the real life or a real world, when someone speaks, I'm going to use a microphone to convert the speech signals to electrical signals. Okay, or a signal that is getting transmitted from a video, an analog signal that is getting transmitted from a video or from an analog television. Okay, or digital data when you want to transmit it over the air. Okay, when you want to transmit digital data over the air, you have to transmit it as a continuous time signal. So in all those places, the signals we encounter is a real signal. So for a real signal, we'll see what happens to the Fourier transform for a real signal. So this is the expression for Fourier transform. You're multiplying x of t with a complex exponential and taking an integral. I'll expand e power j by 2 pi of t using the Euler's expansion, which is cos theta plus j sin theta. So minus, in this case, it is minus j sin theta because there is e power minus j 2 pi of t. So you will get this expression. Now I have a complex number with a real and imaginary part, a minus jb. If I compute the magnitude, I have to square the real part and the imaginary part. Okay. Now when you stare at this squared imaginary and the real parts, if x of t is real, okay, if x of t is real, okay, and what can we say about this function? So I'll what can we say about x of f? Is we have that we have, I mean that's what we have to conclude from this expression. So first I'll actually substitute f equal to minus f. So if I substitute f equal to minus f, cos of minus theta will again be cos theta. So this term will remain the same. Now in this expression, when I substitute f equal to minus f, this term will become minus sin theta. So cos sine of minus sin theta will be minus sin theta. And then when you square it, again it will become plus. So x of minus f, modulus of x of minus f will be equal to mod of x of f. So the magnitude of the Fourier transform is an even function in frequency. So when you have, for a real signal, the magnitude will be a real function. Magnitude will be an even function on frequency in f. Okay, it's an even function in f. So what does this mean is that if you take the magnitude of the Fourier transform, it's just, the Fourier transform in the positive frequencies is just a mirror image of what it is in the negative frequencies. Okay. Now similarly, since it's a Fourier transform we said is a complex number, for every complex number there is magnitude and phase. So to compute the phase, again, since we express Fourier transform as a complex number, we'll take the imaginary part by the real part minus of tan inverse of b by a. No, it's of this form, a minus jb. So the phase is going to be minus of tan inverse of b by a. Okay. So from that, when we compute this expression, from this expression, when we see this expression and substitute f as minus f. So this will become sine of minus theta is minus sin theta, and that so you will get a negative sign here, and this will remain positive. So when you take the negative out, you are going to get plus tan theta. So meaning phase function, when I do phi of minus f, it is actually minus of phi of f. So your phase function is odd. Phase is the phase of the Fourier transform actually is an odd function of f. So that's what this tells us. Okay. So now I'll combine both of these facts together about magnitude and phase. So what I get is that if I take the signal x of f, its magnitude is same, of course, but then the phase is negative of each other. So for example, when I'm substituting in this, so I'll write x of f can be expressed as mod of x of f, the magnitude of x of f, and e power j phi of f. I'll write minus j phi of f to denote the phase as negative. Okay. Now, what happens when I substitute x of minus f? When I substitute x of minus f, this is going to be mod of x of minus f into e power minus j phi of minus f. Now this is same as plus f, mod of plus f, and this term is going to be e power plus j phi of f because phi of minus f is minus of phi of f. Now this is nothing but if I started from x of f, which is mod of x of f into e power minus j phi of f, it is plus j phi of f, so it's a complex conjugate. So it will be simply x star of f. So we get this result, x of f, x of minus f is simply x star of f, which is conjugate of x conjugate of f. Okay, it is complex conjugate of the positive frequencies. What it means is that the negative frequencies are complex conjugates of the positive frequencies. Okay, or similarly, I can say that x of f is x star of minus f, or the positive frequencies are complex conjugates of the negative frequencies. So if you know the Fourier transform, so I'll just show what this means is that, let's say we know the Fourier transform of a signal for positive frequencies, then for a real signal, the negative frequencies are also uniquely determined. Even you just need to know only half the information. You just need to know about the positive frequencies. Negative frequencies, you can compute the Fourier transform by just complex conjugating the positive frequencies. So if you take complex conjugate of this, you're going to get x of minus f. Okay, it exhibits conjugate symmetry. So that's what this tells us. So for a real signal, okay, Fourier transform exhibits conjugate symmetry. So the positive frequencies will be just conjugates of negative frequency. Now we'll impose few more conditions. What happens if the Fourier transform, the signal is both real and even? So if a signal is real and even, if you just look at this equation, okay, x of t is now a real function and an even function. So if x of t is real and even, the first term I'm multiplying even, cos is an even function with an even function, so the result is also an even function. So we'll get 2 integral 0 to infinity x of t into cos of, I'll write it as theta of t into dt. Okay, 2 pi epsilon t, I wrote it as theta. Now this term, x of t is even function, but sine is actually an odd function in time. Okay, again, you know what is odd and even functions. So if you look at the function, you can tell the function is odd or even by looking at the behavior of the function at origin. So for an even function, if you look at the even function, it will have mirror symmetry around the origin. F of x will be equal to f of minus x. For an odd function, it will have antisymmetry around origin. So it should be f of x equals f of minus of f of minus x. So from that, we can say that when I integrate it, so for example, for an odd function, when you integrate an odd function, the positive area will be equal to the negative area. So when you integrate from minus infinity to plus infinity, the value of the integral will be 0. Okay. So from that, we can say that the value of this integral will go to 0. So the complex part of the Fourier transform becomes 0. Okay. Imaginary part of the Fourier transform becomes 0. So the Fourier transform is purely real. Okay. That's a very interesting property. And we already know the magnitude of the Fourier transform is even. Okay. And since it is purely real, there is no phase. Okay. So we can say that the Fourier transform itself is real and even. So for a real and even signal, the Fourier transform is also real and even. We can directly say that the Fourier transform is also real and even. And for a real and odd signal, the Fourier transform is purely imaginary. We can actually see that the Fourier transform is actually, again, this can be very easily proven in this result itself. If you actually take, yeah. So from this expression, for a real and odd signal, okay. So if since x of t is an odd function multiplying with an even function, the result will be an odd function. Odd into even is odd. So the integral, this integral will go to 0. Now because x of t is odd, this is also odd. Odd into odd is even. So this term will become, so this term here will actually be an even function. So we can write minus 2j integral 0 to infinity x of t into sine 2 pi of t. So that's what I've written here. Okay, I've missed a minus sign. I've written a minus here in the equation. Now, if you see, your Fourier transform is purely imaginary. Okay, your the Fourier transform of this function is actually purely imaginary, and magnitude is even. I mean, we can see that the magnitude is purely even for this function. Okay, and yeah, so that's so these are the two things we can say from the signal itself. Now we will discuss about the Fourier transform of some popularly signals we popularly encounter in the communications literature. So the first is an impulse. So it's also called as white signal, signal with a white spectrum. So the Fourier transform of an impulse is delta of t. You can easily show that if we can apply delta of t in the Fourier transform integral, you will get this. If you are applying that, you will get that. So the interpretation is that the Fourier transform is 1 for all frequencies, meaning it's called white spectrum because white is nothing but you mix all the colors in equal proportions, you will get white color. So it's called white spectrum, okay, when it has equal energies at all frequencies. The Fourier transform is magnitude of the Fourier transform is same at all frequencies. So you can see that impulse function can be constructed from narrow pulses of negligibly small widths, say, and then amplitude is inversely proportional to the width of the pulse. So you can actually see that it's a real and even function. So that's why Fourier transform is real and even as well. It's one and it's same in both the sides of the f equal to 0 line. Okay. And the other Fourier transform of a signal is u of t. Again, step function you can find if you integrate. There is an integration property in which I don't have a slide for it. So, but if you have a signal x of t, whose Fourier transform is x of f, then if I integrate the function x of t, the Fourier transform of that signal is given by x of f by j 2 pi f, plus there will also be some term which is x of 0 into del of f by 2. Okay, this is the expression for the Fourier transform, okay, for of the integrated version. So if you directly substitute it, you will get this expression. So you will get half into delta by 2 into 1 by j 2 pi f. I'll revisit this signal a little later, but first let me finish off some important functions. The other function is the pulse function. That is, if a function exists for a short duration, this is a very important function in digital communications. So if a function exists, it's 1 for an interval minus t by 2 to plus t by 2, which is the on time, the width of the pulse is t seconds. The Fourier transform of this function is a sinc function. Okay, a sinc function is a sinusoid multiplied by 1 by f. For example, it is like of this form, sin x by x. So you take a sinusoid, multiply by 1 by x, which is a hyperbolic function. Then you will actually, what you get is a sinusoid which is actually going to decay down as 1 by x. Okay, so if you take this is the function. Since it's an open book, you don't have to remember, but if it's good that if you have this equation handy. So you'll get t sinc pi f t. I have written sinc x, the definition of sinc x as per this equation. Sinc of x is sin x by x. Okay, so in some books, sinc x is defined as sin pi x by sin pi x by pi x. Okay, I'll let's follow this notation. Actually, I've written it as sin x. Sin x by x in the here, but this is the notation I'll most probably follow in the class. I'll just mention it. Even if in the quiz, if I'm questioning it, I'll definitely give this way. This is the definition of sinc. Whatever the definition of sinc x that I use, I'll give that very clearly. Next, there is another very important property called the frequency shifting property. So if I multiply a signal in frequency in time domain by a complex exponential 2 pi f naught t, okay, then let's say x of t be a signal, I multiply it in time domain by a complex signal, okay, then the Fourier transform of this signal is given by x of f minus f naught. You can very easily show this. So Fourier transform already is e power minus j 2 pi ft. So since I'm multiplying it with e power plus j, 2 pi f naught t, so you'll get f minus f naught into t. So you can write it like this. The integral of Fourier transform will become like this. So this is simply, instead of f, I have substituted f minus f naught. So this becomes x of f minus f naught. So here is an interesting thing to see from this equation. So let's say x of t has a Fourier transform centered around origin. It's a real signal. X of t is a real signal. So we know that its Fourier transform is going to be, I'll plot the magnitude Fourier transform. It's going to be symmetric around the origin. Now, when I say x of f minus f naught, after multiplying with a complex exponential, the Fourier transform is now going to be centered around f naught. Okay, origin is here. It's just going to be shifted to f naught. Now, if you see this Fourier transform, it doesn't exhibit even symmetry around origin anymore. The magnitude of the Fourier transform. Okay, it no longer exhibits even symmetry, right? Meaning it is no longer symmetric. There is nothing on the negative axis. The negative frequency axis. For f less than 0, the Fourier transform is completely 0. It exists only here. So now the signal has to be complex. It cannot be a real signal anymore. And that's what we see here. When I multiply x of t with a complex exponential, the signal becomes complex. So you can see that the Fourier transform exists only for positive frequencies. Okay, negative, the Fourier transform doesn't have any mirror symmetry around origin, the magnitude of the Fourier transform. Okay, so using that, you can actually very easily show that, this can be written as actually x of f convolved with delta of f minus f naught. Okay, so multiplication, there is a very interesting property called multiplication in time domain as a convolution in frequency domain. So you can, from that itself, you can directly say e power j 2 pi f naught t will have a Fourier transform of delta of f minus f naught. So for e power a complex exponential of this form, which is e power j 2 pi f naught t, the Fourier transform will be an impulse centered at f naught. So similarly, e power minus j 2 pi f naught t will be an impulse centered at minus f naught. So again, if you observe, both of them are complex signals, so the magnitude spectrum is not symmetric around origin. That is f equal to 0 point. Okay. So from the knowledge of plus and minus, if I want to construct a sinusoid, which is a real signal, cos of 2 pi f naught t, it's a real signal, that will be obtained by adding half of this and half of this. Half of this and half of this, adding it together, you get it. So in that case, the Fourier transform for this signal, because it's a real signal, it's going to be even symmetric around the origin. Okay, so now again, if you remember, cos 2 pi f naught t is a real and even function. Cos x is an even function, right? Your cosine function. At the origin, it will be like this, near the origin. On the other hand, the sine wave, the sine function, it's an odd function. Okay, near the origin, it is an odd function. So if I want to construct a sinusoid, I need to use e power minus j 2 pi f naught t. You'll have to subtract the two functions. I mean, you'll have to subtract e power plus j 2 pi f naught t minus e power minus j 2 pi f naught t by 2j. Okay, so for positive frequencies, I will get 1 by 2j as the coefficient, and for the negative frequencies, I'll write it in a different color. Okay, I'm sorry. So I'll probably plot it in a different axis. So this will be 1 by 2j. The Fourier, I'm just plotting not the magnitude, but I'm plotting the Fourier transform itself. And for the negative, it's going to be minus 1 by 2j. Now, if you see, the Fourier transform is purely complex here. Okay, the Fourier transform is purely complex because we discussed sine function is a real and an odd function. For a real and odd function, Fourier transform is purely imaginary, and that we can see here. Of course, magnitude, since it's a real function, magnitude is already always, even symmetric. That is, it is symmetric around the origin. Okay, and you can very easily see that the positive and negative frequency energies are complex conjugates of each other. Okay, that directly comes from the condition that the signal is real itself. The additional constraint that the odd function poses is the Fourier transform being purely imaginary. And I'll leave it with another very important function, mathematical function, which we'll be discussing, is the Gaussian function. This is a Gaussian function, and I've chosen this function such that the area of the function in time domain is 1. Okay. For those of you who have done basic probability and statistics, you would know that this is a Gaussian function with zero mean and a variance given by sigma square. Okay, in time domain. The Fourier transform is also a Gaussian. This is a very interesting property. So Gaussian is the only function whose Fourier transform is also a Gaussian. Okay, for no other function, this condition is satisfied. Okay, of course, the shape can be the variance will be different. Okay, the variance is definitely going to be different once we go to the frequency domain. But the nature, the function will remain the same. It will be a Gaussian. So if the time domain variance for this function is going to be sigma square, in the frequency domain, it depends on how it is in time domain. For example, for a very narrow function, say for example, your Gaussian sigma is very small. So then the function is going to be very narrow in time domain because the area is supposed to be 1. I'm just showing it as the peak is going to be larger. Then in frequency domain, it's going to be wider. It's going to spread. Okay, it will be more of a wideband signal. So often you encounter Gaussian signals in pulse shaping systems. Okay, later we'll discuss what is pulse shaping in digital communications. In pulse shaping circuits, we encounter Gaussian functions. Okay, so this is also, I've just shown this, probably it's not proper, but this is a Gaussian function with a very large variance. Okay, this is also a Gaussian function. If you expand it, your Gaussian function is going to be narrower in frequency domain if it is wider in time domain. Okay, so that's the important thing. You can see that from these expressions itself. You can see this here itself. The variance here is 1 by 2 sigma square. It is proportional to, I mean, sorry, the variance here is sigma square. It is proportional to 1 by sigma square, proportional to. Okay, so from that we can say that if sigma is low here, 1 by sigma is going to be very high. The frequency domain spread is determined by 1 by sigma. Okay, and this is often used Gaussian. It's called, there is something called Gaussian pulse shaping. We use it in Bluetooth. The Bluetooth transmitters use this waveform. So it's a very interesting waveform. I'm not going to prove this. Probably I'll give it as a tutorial problem. So this result, it's a very interesting proof. You can try it out by yourself. Okay, or I'll try to give it in one of the assignment tutorial problems. Okay. Now we look at some properties. We just saw some very basic properties of Fourier transform. Some important properties which will be useful in communication systems is, one property is called the duality. So if you know x of t, x of f is the Fourier transform of a signal, which is given by integral minus infinity to plus infinity x of t into e power minus j 2 pi ft dt. Okay. Now I'll substitute from, we also have the synthesis equation here. So your synthesis equation is x of t equals integral minus infinity to plus infinity. Okay. Capital X of f into e power plus j 2 pi ft dt. This is your synthesis equation. Now I'll take the Fourier transform and change the variable f to t. Okay, it's just a mathematical function. So I'll just change x of t. Then what happens to this function? Now I'll replace this x of f by t, capital X of t. Okay, and t by f. So we'll replace f by t and t by f. So I'll make a substitution, t equals f. Then you will actually have x of f. We'll see what this is, equals x of t e power j 2 pi ft. There is f and t, I've replaced it, and this becomes df. Okay, now you have the integral as it is. Now this looks like a Fourier transform of a time domain signal. Okay, this sorry, this is actually df here. This is for another synthesis equation. So instead of f, I'm substituting f as t. The substitution I'm making is f is t and t will be replaced by f. So df will become dt. So this looks like an equation whose time domain signal is x of t, and I'm computing its Fourier transform. The only difference here is that the value here, it's positive, it's e power plus j 2 pi ft. To get that minus, I can say that the Fourier transform, it is nothing but a Fourier transform of a function, which we will call it as x of minus f. Okay, so if you look at this, if I just I've just replaced the variables here. I've just substituted t equal to f. Okay, so I'll get an expression. If I substitute f as minus f, I'll get this equation. Okay, and my f as minus f on both the sides, I'm going to get this. Okay, I think if that was not clear, let me just see. First, what we did was that we made t equal to f and f equal to t. It's just a variable substitution. I got this result, x of f equal to this. Okay, this was plus here. Now I'm going to substitute f as minus f. The next substitution, it's all just a mathematical variable. I'm just going to make it as minus f. So this becomes x of minus f. Now if you look at it, this is our familiar Fourier transform expression. So I can say the signal x of t has a Fourier transform of x of minus f. Capital X of t has a small x minus f. Okay. So this property is called duality property. Okay. So which means this is a very interesting property. So from that we can solve quite a bit of problems very easily. Complicated problems can be reduced very simply using this property. So for example, when I have, say for example, I have a pulse function. We know the Fourier transform of a pulse is a sinc. Okay. So similarly, if you are to directly compute the Fourier transform of a sinc function in time domain, it will be a little bit complicated. I mean, you have to do a complicated integral. You'll have to solve a complicated integral. But using the duality property, I can very easily, I can actually, okay, using this duality property, I can very easily say that I have just, if a signal is, I mean, a sinc function in time domain, in frequency domain, you just have to repeat the function. I mean, you have to just take x of minus f. You have to just mirror image it around origin. But if it's an even function in time domain, it will be an even function in frequency domain as well. So for a sinc function, the Fourier transform is a pulse function. Okay. And one other important property which I forgot when I was mentioning sinc functions. So whenever you have a sinc function, how do you interpret the results? Is that, as I said, it's one of the most commonly encountered functions in digital communications. If I have a pulse of width t, then the Fourier transform is going to be a sinc function. Okay. And the zero crossings of the sinc function, the first zero crossing is going to be at 1 by t, and this will be minus 1 by t. The second zero crossing will occur at 2 by t. In fact, at every integral multiple of t, 1 by t, which is k by t, there will be a zero from the sinc function. And you can say most of its energy will be contained within 1 by t and minus 1 by t. But still, in digital communications, what we do is we do something called pulse shaping. Okay, for a rectangular pulse, the Fourier transform is a sinc. So if I choose some different kind of pulse shapes, I can guarantee that most of the energy will be contained within the symbol interval, which is, within the symbol bandwidth, which is 1 by t. Okay, this is called pulse shaping. We'll discuss about that later. Okay, yeah. So this is duality property. So if you from duality property, you can say very interesting things. We know the Fourier transform of an impulse is a constant, and similarly, in time domain, if a function is DC, the Fourier transform will be an impulse. So it's a DC signal, so all its energy is concentrated only at origin. Okay, so that's what it means, and you can actually see there is a very interesting interpretation for a DC signal. So how do we construct a sinusoid which is cos omega naught t? Okay, so that let's say we have a sinusoid of magnitude A, then we know that the Fourier transform is constructed using two complex exponentials of width half and half, and each centered at, this is 2 pi f naught. So let's say this is 2 pi f naught t plus f naught and minus f naught. A by 2 and A by 2. I'm sorry. This is A by 2 and A by 2. Now I can call this as a DC signal if omega naught is 0 or f naught is 0. Right? If f naught tends to 0, then this becomes a DC signal. Right? Though if omega, this term cos of 0 is 1, so you get a DC signal. Now I'll slowly keep reducing f naught, slowly towards, I'll approach it to 0. So what happens to these impulses is both the impulses will move closer towards the origin. Okay. And finally, both the impulses will meet and add at the origin, and you will get an amplitude A. Okay. When f naught becomes 0, both these impulses will just collide at origin, and the value of the impulse will become A. So for a DC signal, the Fourier transform is just an impulse at A. So that should make also, it should make proper sense. You can visualize it as a sinusoid with just one frequency, which is 0. Okay, so all the power will be focused on a single frequency. Okay, so that's it about the interpretation here. And the next result, okay, again, we use this Fourier transform properties to show that, let's say, for example, there is something called time shifting property. I mean, when you multiply a signal in time domain, so for example, if I have a signal and I multiplied it by e power j 2 pi f naught t, you will be frequency shifting it in frequency domain. Okay, so using that, I'm sorry, that's nothing to do with this. So, for example, we discussed in the last, in few moments ago, if I have a signal of this form, e power j 2 pi f naught t, the Fourier transform of this signal was actually delta of f minus f naught. Okay. Now I'll take a similar function and replace f with t and call it t minus t naught. What will be its Fourier transform? So you'll have to take this function. It's very similar to this. Okay. I've just substituted f equal to t here. The Fourier transform of this is going to be, I've done, this is capital X of t, so you have to get x of minus f. So you have to substitute t as minus f. So you will get minus j 2 pi t, and your f naught is actually corresponding to t naught here. So t will become minus f and it will be t naught here. So you can see it that if it's complex exponential and frequency domain contains an impulse, a time domain impulse function will have a complex exponential in frequency domain. So that's what it means here. Okay. And the other important property is multiplication property. When you multiply two signals x1 of t into x2 of t, the Fourier transform of the resulting signal will be simply convolution of the two Fourier transforms, x1 of f into x2 of f. Okay, and using this convolution property, we can show a very interesting result. So if you take the product of the two signals, x1 of t, and integrate it over time, then that will also be equal to the product of Fourier transform and actually x2 of minus f into df. Okay. Now again, you can I've also taken that if x1 of t, let's assume it's a real signal and x2 is equal to x. What I'm trying to show here is that this, I mean, the validity of this expression, we will get integral x square t will be equal to integral mod of x square df. So this is called Parseval's theorem. Okay, I haven't said this. Okay, you can compute the energy of a signal. This is a time domain integral from its Fourier transform itself. Okay, it translates to a very similar, yeah, it's a very similar integral. Okay, so sometimes energy time domain signal can be pretty complicated to integrate, but the integral can become very simple when you go to frequency domain, and that can be solved because of this very interesting property. Okay. Multiplication, you again, when I multiply two signals, it's convolution in frequency domain, and it's very popularly used in communication systems. It's called modulation property. I've shown here, you multiply a signal x of t with a cosine signal, your signal spectrum will be shifted. So if I have a Fourier transform of a signal, say centered around origin, when I multiply it with a complex, sinusoid cos 2 pi ft, it will get shifted to two different frequencies, f naught and minus f naught. It will be centered around this. Okay. So one part of it will go here and one part of it will go to negative frequencies, because you should remember a sinusoid cos is constructed using two complex exponentials, one at positive frequency and one negative frequency. So that's how you get these two frequency shifts. Okay. So similarly, convolution in time domain amounts to multiplication in frequency domain. This is one of the most commonly used properties in almost every filter and LTI system. We use this. Okay. Again, I have discussed this problem in the class. You convolve to sinc functions, you also get a sinc function as the output. So this is, I mean, what have I covered in Fourier transforms? This is it about Fourier transforms. And in the next class, probably in the next lecture, I'll discuss about the orthogonal signal spaces and how do you visualize a signal as a point in a signal space. Okay. So we'll discuss about that. So this lecture is mainly intended to familiarize you with the Fourier transforms necessary for this course. I've discussed some popular functions, pulse function, and also Gaussian function. You can go through that. Okay, and also sinc functions. Okay, so I discussed this problem in the class. You take convolution of a sinc with a sinc, you get a sinc again, and that's a very interesting property. Only sinc obeys this property. So what I mean is, if I take a signal x of t, convolve it with x of t, I should get x of t back. And here x of t is not an impulse. Okay, if I put a condition that x of t is not an impulse, then only a sinc function can obey this condition. So that's what I've taken an example to show that sinc function can obey this. Okay, and there are many solutions. Almost every, for different values of t, you can show that all the sinc functions obey this property. Okay, so that's it about this. And the next class I'll talk about vector spaces and signals represented as vectors.